Thank you very much, Dean Janda, and I just want to start by alerting you that I'm a newcomer to this field, and I'm mostly a messenger. So if you want to shoot someone, you can shoot me. I think the message is very accurate, but I'm going to go through it quite quickly. I'll assume you can read faster than I can speak. And I want to talk about how we can transition from fossil fuels to something more sustainable. And I'm focusing on the next century because that seems long enough for us to have a breather and think about what we might actually want to do if we want to convert it to be forever. This is what I see the current situation as presenting itself. We are using up and burning up many more resources than we think. Population has tripled from 1950 until now. We wouldn't want it to triple again, I don't think, in another 60 years. So something has to change there. Each evening, 219,000 new people turn up to dinner. Therefore, we have to figure out how to feed them. The only way we're going to feed all these people is with a process like this, the Haber process, that requires incredible muscle, lots of power. The issue is not energy. The issue is power. Power is energy plus now. And that's what's important. There's plenty of energy sitting around, flitting around like butterflies that's useless. What you want is power. That's the difference between a young man sprinting and an older person walking. It's not energy, it's power. 1 out of 2 nitrogen atoms in your body came from this process. So if you think we can do it with organic farming, that's going to be a very big pile of manure that you're going to be staring at there. This book came out in the 70s, and you know, it's not half bad. It seems to have gotten the population thing right. What I don't like is this part, and this part, and this part, and that part. And that seems to be coming sooner than you might like. So the question is, how can we sort of slow down the population growth and then come to some steady state in which people have a reasonable standard of living? And if you look at prosperity and family size, you get an L-shaped picture here. The stable replacement rate is 2.2. It would be 2, except we have motorcyclists and skydivers. And the official prosperity threshold by the United Nations is $7,500 a year. So when people complain that they're not prosperous, you have to keep in mind that most of the world is not at that level, or even close. And just like us, they would like to be. And in order to do so, they're going to have to consume more energy. So if we could get people to be more prosperous, they have less children, and the population just naturally stabilizes. We don't have to do anything else. And there's one outlier here, Saudi Arabia, which looks unsustainable, and that's because it is, because when the oil runs out, that dot is going to move one way or the other. Prosperity, in turn, depends on energy. There's the prosperity threshold, and there's the trend line. That means if you're going to be prosperous, you have to use a certain amount of energy, and that makes sense because you have to be doing something that's worth something, like making a car or running an earth mover or building a building. And you can't do that on batteries or by waving panels around in the sun. You need some power to do those things. Energy use, in turn, is rising. People talk about a quadrillion British thermal units, but basically in the developing world, the energy use is rising and the world use of coal is also rising. And that is bad because it increases the amount of CO2. Now, the Sierra Club would probably have us sitting in the dark thinking about things, but let's imagine that we cut our energy use in half. That would be a major step. Driving half your electric bill. Let's suppose we do that. And let's suppose that the rest of the world agrees to use no more energy per person than that. Then this is what happens. So my conclusion here is that only if the rest of the world is willing to live in relative poverty will energy use be curtailed. And I don't see any evidence that people are different anywhere else. Nobody likes to be poor. They would like to turn on a light bulb, and if 1 million people in India turn on one light bulb, and I put on a few solar panels on my roof, this is what happens. They are already not using any energy. They're in the dark. So what can we do? Well, we could price everything so that we'll be out of business. Or we could just wait and we could hope that the CO2 thing is a myth or a hoax. Or we could try to do something. But the only thing we can do that makes any sense is to have a cheap, huge, reliable, and safe source of electric power that's always on and makes no carbon dioxide. Anything else won't work because the poorer countries will burn coal and the ocean will rise here. So we need something I call deep green. And my argument today is that wind and solar are probably not going to meet our needs, and that the other forms of renewable energy aren't even close to what we need. This is one projection, which I don't like. People argue that if there's climate change, there'll be winners and losers. The problem is we're the losers. This is 2100. The entire US is uninhabitable desert. The entire part of Mexico is uninhabitable because there are hurricanes all the time that knock your house down. There isn't a drop of water, and so people have moved because nobody lives in the Sahara Desert or the Gobi Desert now. I just brought these things up to show you what the prediction is. I don't like this one. Western Antarctica, unrecognizable, densely populated with high-rise cities. That sounds like World War III to me because nobody owns Antarctica. How does desertification happen? Well, here's how. You can put as many Caterpillar 623Bs against this thing as you want, and you lose. And if you lose your farm here, and you're forced to move, and you lost your way of life, and your land, and all your ability to earn income, you just go to the city with your hat in your hand because you're broke. You've basically lost everything you worked for. This is what the Nobel Prize winner Paul Crutzen says: I'd like to be optimistic, but I have no good reason to be. To be safe, we should cut our emissions by 70%. We're currently putting in more. Some people don't believe that we're the cause, but if you look at the CO2 concentrations, something happened around 1769. That's when James Watt invented the steam engine. The steam engine ran on coal and had incredible power. It had 3 horsepower. Watt worked out that a good horse could pull up 330 pounds of stones 100 feet in a minute. And that's what he called 1 horsepower. And he had this little thing that had 3 horsepower. It was amazing. And the first thing the English did is they pumped all the water out of the coal mines, and then they went wild. And people got a lot richer. But London was black with coal dust, and you know what happened. And if you zoom in, you see that there was a huge change there. And it agrees with how much we've burned. The economic cost of this could be large. If the sea gets rougher, there's more storms and higher tides, you're going to have to build barricades, and you may have to move. And if you have to move, you have to ask who's going to buy your place. Not me. And I'm not moving to Dallas. Here was Dallas all July. 100, 100, 100, 101, 105, 105. It got down to 86 in the middle of the night. I guess you can keep the air on, but guess what? To keep the air on, you need power. And if you need to keep the air on at 86 for the whole city, all 24/7, all summer, you need a lot of power to do that. We're starting to see this used to be a lake. And of course, if you've got a lake, even if you've got super scoopers, if the lake's dry, it's hard to put out fires. Fire danger here is an ongoing worry if it keeps getting warmer and warmer. Well, this is one solution. Here's a really nice looking installation. They look great. But solar has no power. That's why they talk about solar energy. Because it has no power. And to prove this, let's just answer this question. What area in solar photovoltaic panels would we need in Indio for a 1 gigawatt power plant? I'll let you guess. Well, rather than guessing, let's do the calculation. A good panel produces 1.2 watts per 100 square centimeters. So for a gigawatt, it appears we need this number of square feet. However, we lose with AC-DC conversion, and the sun isn't always shining, so we lose another 80%. And so we need 500 million square feet, and that's 18 square miles of solar panels. Even if we do this, then at night, what do? This is material which a professor in physics posted, and it's very, very topical. The Million Solar Roofs initiative sounded great, but it just doesn't make any economic sense. When you go through the numbers, you're effectively subsidizing wealthy people like me who can afford to put those panels on, and making ratepayers and taxpayers foot the bill. And when you figure out how much power we get 600 megawatts of electricity from our Million Solar Roofs, and that's about half as much of a nuclear reactor that costs half as much that's always on. And it's also only 1.2% of what we use, which is 51,000 million watts of electricity. That's just California. You can build more efficient farms, but they have their own environmental toll because they're enormous, sprawling things that go everywhere. This is one approach they took in Spain. If you like to go for a hike, then this is not the greatest thing. Somebody has to keep these clean. I don't know who does that. If you look at the economic cost, it's been a disaster, and it has been here too with companies like Solyndra. It doesn't need to be, but if you go too aggressively and you just hand out money to every kind of scheme, it might be. So they put a ton of money in, but they get no power out, and so their money that they owe is now just debt hanging over them, and these things they've installed don't supply any electricity for them. So it's not enough to have a job. I can have a job dealing drugs, but that's a destructive job. And I can also dig a ditch with a teaspoon and keep filling it up, and you can pay me to do that, but that's not going to do anything. You've got to really make something that's worth something, much more than the effort you put in. The energy is not free, and it takes a significant amount of energy to create the solar cells. I won't talk about concentrated solar, which makes more sense to me using heat. That also needs big areas of land, and the heliostats need to be kept clean. What about wind? Well, wind only produces power when the wind is blowing, and last time I checked, we don't know when that is. So in case you're having open heart surgery and the lights go out in the operating theater, you can blame, sort of you've been lulled into death. So we need a backup power source, and that's natural gas when the turbines are not operating. So you have to build both of them. And it turns out the natural gas is more inefficient when it's in conjunction with wind than it is by itself. So you're better off actually, from a carbon standpoint, just putting in natural gas and forgetting about the wind. Putting in wind and natural gas is like starting your car up, driving at 2 feet, and then turning it off because now the wind blew. Then you sail forward a few feet, then you start your car up again, turn it off. The mileage you get is terrible. It can be much worse than driving steady, especially with a combined cycle natural gas plant. And you need 10 times the amount of steel and concrete to do that. And that has an environmental toll. Furthermore, the wind turbines require a rare earth element, neodymium, for the high-strength magnets. And there's only one place you can get it, China. So if you think wind is going to reduce our dependence on foreign powers, you're completely wrong. It increases our dependence on foreign powers. Landowners, if you talk to them after they install the project, they don't like it because humans don't like something big moving above them that looks like a Tyrannosaurus Rex. It bugs you. And if it strobes your house so you can just be at a disco all day long, that bugs you too. And you kill a lot of flying animals. Bats I'm not so worried about, but golden eagles I am. This is energy farming, so you need huge installations. Transmission lines are also an issue here. People don't like transmission lines through their property. This is the Kern County project. It's going to have a very large footprint out in Tehachapi. Oh, after our big ramp up, how much zero carbon power do we get from solar and wind? The answer is we get about 2%. And that's why I claim they have no power. The U.S. Department of Energy funds all these things. As you've seen, they fund everything they can think of. If I have a project to turn manure into gold, they'll fund it. Here's their levelized cost. What they call advanced nuclear is still based on uranium. I'm going to argue that we can go much cheaper than that. It's going to cost you a lot more if you use these things unless they come down in price. And ratepayers care about price. Now they had this article that ratepayers, Edison's being guilty, and they, greedy rather, and they show this San Onofre nuclear power plant, but it actually has nothing to do. This is just a stock photo that the LA Times had. The real reason that it costs more is that Edison's upgrading everything. They put in 308,000 transformers, 87,000 power poles, and so forth and so on, and it has nothing to do with a nuclear power plant. So let's talk about nuclear power because it does have power. And there are two kinds, fusion and fission. And fusion's never worked. And so I'm going to just forget about fusion. It's not going to work in time. It's never worked so far. They've put in a lot of effort. There are a lot of smart people there. It's a difficult problem. Fission does work, and fission is the splitting of a large nucleus into a smaller one. And here is how it looks. It splits into two unequal fragments, and we get out some neutrons, and the neutrons then can hit other nuclei, and we get a chain reaction. And it was an accident that we even discovered this, because the only fissile element, which is U-235, had almost all decayed away. So it was almost a miracle that we found this out. Uranium-238 won't fission, but if it does capture a neutron, it will eventually produce plutonium, which is fissile and unfortunately is a risk for atomic weapons. You don't want plutonium to go missing. There are only 3 fissile elements, 235, 239 plutonium, and 233 uranium, which you haven't heard of because it's so radioactive it's all decayed. But 233 uranium is what I want to use for the new generation of power plants. Only these two have ever been used for weapons, and there's a darn good reason why, and that's why we've picked this one. We don't want anybody to use our power plants to produce weapons. And we can make uranium-233 from thorium. There's one isotope of thorium-232. The US has it in huge abundance, huge. We have lots of it. It's very cheap. And it's so safe that they used it in Coleman lantern mantles when you went camping. That brilliant, bright, white light, that's thorium oxide in there, giving you that. And it has it's the best fuel. In other words, it's the hardwood of these woods. It burns nice, clean, beautiful. However, because in the 60s, when Oak Ridge National Lab was looking at this, it didn't seem likely that we could make weapons, they abandoned the project. Because the idea in the 60s was to make more weapons than the Russians. And we made tons of weapons, and now they're all sitting around. Somebody has to mind after them. We don't want them to go missing. Those weapons work. If you aren't worried about weapons, you should not be worried about power plants. You maybe could divert fuel, but you can't make a bomb out of it very easily. You need to really work to make a bomb. The way you do it is the way they're doing in Iran. You purify uranium ore. Thorium, there's no way you can make a bomb, and that's because when you make this uranium-233, you produce some 232, which is a strong gamma emitter. And that means it's impossible to steal the fuel, because you basically have a big light on wherever you go saying, hey, I've stolen fuel. And I can see this from miles and miles away with any radiation detector I've got, and there's no way you can hide it. You can put it in as much lead as you like in a rail car, and this thing will come zinging out. And the other thing is that it makes it very inconvenient for you to handle it, because if you get too close to it for too long, you get into trouble from the radiation dose you get. So that's why they don't use this to make bombs. It's too inconvenient. And in addition, we're going to use a very hot molten salt as the nuclear fuel, and it's at extremely high temperature, so you can't get anywhere near this stuff. Oh, here's the periodic table. Here's the natural one you can mine and isolate. Here's the one that's been used for atomic bombs, and here's the one I'm proposing to use in the future. And you can breed these by adding a neutron to thorium. And you can breed plutonium too from uranium-238, but I prefer this because this has no weapons potential. So we can make endless 233 fuel. We run our reactor and we have a blanket of thorium around the outside. the neutrons come out here, some of them hit the thorium, make uranium. We isolate the uranium, we put it back into the core, and we run it. And the only thing we bring to the reactor is thorium. So we go get a lot of Coleman mantles, and we bring them and put them in the reactor. And we can transport thorium anywhere. It's lying on the ground in Idaho. It's not dangerous. It's everywhere. If you could make anything, a bomb or something out of it, I assure you people would have done that long ago. And for that reason, this is completely safe, and we can sell this device to anybody on Earth and not worry about them somehow doing something bad with it. So we breed uranium from thorium, and we just have this liquid fluoride molten salt, and the reactor is completely stable because heat expands the salt and then it slows it down. And it's very hot, so we get very high power conversion to electricity. And we can also produce hydrogen, ammonia, and we can desalinate water for free using the waste heat. And we can desalinate a lot of water, plenty of it. And the last thing is that the long-term radioactive waste is less than 1% of the current power plants. So 1 ton of thorium will power the 1 gigawatt plant for 1 year. This is my lifetime energy usage, this pinball of thorium. And I will have a great life using this. I'll have things on that I want on, and I'll be driving everywhere I want to go, and this is all I will use up. And that's the difference between this technology and natural gas or coal. We have many, many hundreds of thousands of tons of reserves. And a ton is only a half meter because it's very dense. So this is your power plant for the whole year. We have enough thorium in Idaho to last 5,000 years with no conservation. It's all ours. We don't need to go anywhere else. And the other thing that's interesting is this analysis by Robert Hargraves that it's cheaper than coal. So this is an analysis of setting up a 100 megawatt thorium power plant. And this is the real advantage, is that we can undercut coal, and so poor people can have clean, abundant electric power. And this is the answer to the first riddle that I started the whole talk with. Unfortunately, this is the only answer, because the other things are more expensive than coal, and therefore poor people cannot afford them. How many coal-fired power plants are being built in China each year? 1 a week. So they're building 50 a year. That's adding a lot of CO2 into the atmosphere. The difference between this technology and a conventional reactor is a conventional reactor has water under pressure and needs a huge vessel. And if it keeps heating because you lose cooling, you've got a problem, because anything under pressure that keeps heating is basically a bomb. The fuel rods have to be taken out because they're encapsulated and sealed, and you get damage. You don't want to risk the stuff getting out into the water. The molten salt thing has no pressure. This is like taking table salt and heating it up so hot that it melts into a clear liquid. It still has no pressure. You're going to have to heat it unbelievably hot to get it to boil. So therefore, you don't need any big containment vessel. Therefore, this whole thing is tiny. And you just bury it underground, and it's out of your hair. Takes no land at all. And the only thing we add is thorium, which we've got. If we look at mitigating CO2, just compared to natural gas. Natural gas is supposed to be clean, but it still produces CO2. And 1.3 million metric tons don't go up because of the current U.S. fleet of 104 nuclear power plants. This is the radioactive waste issue. Thorium is down here in producing actinides. And these purple ones are the ones that people say, gee, we'll have to store this thing 100,000 years. How are we going to do that? Well, we don't produce the purple one. We have to store things 100 years. Just keep them away from people. Just keep them actually buried underground where they already are. Just don't dig it up and eat it. Okay? That's all you have to worry about. And we can build things that last 100 years. That's no problem. We can mass produce them. If you go to a talk on solar power, one of the comments that makes people slump is that we would have to build one nuclear power plant per day for the next 5 years to make any difference. Well, guess what? Boeing builds one plane a day. Planes are more complicated than these things, and they have to work. And Boeing's one company. And we're talking worldwide. We can easily build one power plant a day once we standardize the design like they've done here. To his dying day, Dr. Teller advocated thorium. I wondered what this strange symbol was, and that meant deceased. So out of the grave, he's still advocating thorium. Published in 2004, the power plant could operate for 200 years, etc., etc., etc. Nothing was done. This was 7 years ago. But in China, something is being done. Now this is, again, a stock photo of a power plant in Ohio, or Michigan or somewhere. But these are the comments that they say. China read the Oak Ridge National Lab reports, which are posted online. Their scientists said, this sounds interesting. They have a smaller regulatory burden than we do, and they're starting to do experiments. Turbine design has also made some major advances. And with these incredible high temperature salts, you can use a supercritical CO2 turbine. And so you have something about the size of this room buried 10 meters underground that can power all of Orange County for 40 years. So here's my summary. I think we've got a solution. I think it'll work, but we need to do more work. We need to actually make prototypes. We need to see how they behave. We have to make absolutely sure they're 100% safe. I think, for the reasons I've argued, that they're much safer than other options, but we need to verify that. We can't just guess about it. We have to make them and do it. And we have a good group of people here who are interested and they believe in what they do, and I think we've got quite a good program going. Thanks so much for your attention.